Okay, for people joining this live stream, this is a working session with a slightly different group of people than we've typically had. We are interested in understanding how calculus can be generalized to deal with the kinds of things that show up in our models. And let's just get a kind of a motivating example here. Let's say we have let's take the example of, where's a good example here? Oh, here's some good ones. Let's say something like this, okay? So we've got, this is a structure that we claim limits to something. And the question is, how do we do the analog of calculus on the limiting object here? I don't know why this is so slow, but something weird going on with my computer. Let me try and resolve that.
So just to set the stage, maybe we should clarify what type of calculus we are talking about. There are several types of calculus, right? Besides what is called infinitesimal calculus, which is the main part of differential and integral geometry. There's also calculus of operators, the calculus of algebraic objects, propositional calculus. In fact, in our models, the ZX picture, the quantum mechanics picture, is a ZX calculus. It's a calculus of operators.
Right.
So there are already many types of calculi that are there in the models.
So what I'm interested in is what ends up with differential geometry on these kinds of objects. So imagine this thing. Let's just, you know what? This is just driving me crazy. Hold on one second. I'm going to quit this. Oh my gosh. Something has gone very wrong here. Hold on one second. Let's just quit. Wow. Okay. So the thing I'm thinking about is, imagine we have an object like this. Imagine that this was a an alternative version of something like this would be what we get in how do we get a let's see, discretized region of a disk, for example. Right, what we're used to there is, okay, there we go. So in a case like that, we're pretty confident that we can build up all of differential geometry on something like this as it limits to smaller and smaller triangulations, right?
Right.
Okay, what happens on an object like this? Right, so this object, we know if we compute all kinds of different things, we can compute curvatures, we can compute all kinds of differential geometry kinds of things, and all sorts of differential geometry results will just apply to an object like this. The question is, in the limit of this, if we run this not for 13 steps, but for 10,000 steps, and it's a great big object, we can compute certain kinds of things on this object. How do we set up all the apparatus of differential geometry, leading us eventually to things like fiber bundles and all those kinds of things on a system like this? That's what I'm interested in here. Right? Does that make sense?
Yeah. Okay.
So I mean, go ahead. What we know is that there are some cases where we have, a thing like this guy, for example, where we pretty much understand what kind of a thing it converges to. It converges to some kind of lattice-like thing, right?
Mm-hmm.
And but the question is, in the more general case, where it isn't necessarily an integer dimensional thing or anything like that, what what can we say about what's going on? Am I making sense?
Yeah.
Okay, so I just want to make sure. So in this case, are we assuming the combinatorial metric? Or are we making space for more broad interpretation of metrics on these structures?
I don't know yet. Let's start off by assuming. I don't know what you mean by combinatorial metric. If you mean graph distance as a basic distance metric, then that will be the first assumption. Okay, so let's set that stage a little bit, because that is an approximation to what we imagine is really going on. So let's set a stage of something. Okay, that's a good point, and let's talk about that for a second. Okay, so I just want to point out. Let me show something here. Something I did in this piece here was to ask the question. Okay, so what is the relevant lowest level metric? Okay, so the first thing we're going to do, first thing to study is spatial hypergraphs. But spatial hypergraphs are a fake at some level, because they are in some foliation, they're a particular time slice of this causal graph. They are reconstructed from a causal graph. And the better thing to do would be to have, and I think I had some here, to actually look at these reconstructed graphs. Does that make sense? Right? So did you understand what I'm saying? John,
not quite sure I'm there yet.
Okay, so here's what we're doing. Right, so here's what we're doing. So this is the evolution of a spatial hypergraph with a particular updating order. Okay, you understand that?
Mm-hmm.
Okay. There's a question of, if you looked at the reconstructed, okay, so this is the analog of a branch field graph deduced from a causal graph, a space-time causal graph. Does that make sense? So in other words, 2 points are connected here if there is a light cone 2 steps back, for example, which reaches those 2 points.
Yes, that makes sense.
Okay, so that is in a sense a more realistic reconstruction of space. This reconstruction of space is some kind of instantaneous space-like hyperchain. Am I making sense?
Yes, so Jonathan calls these space-like hypersurfaces, actually.
Which things? These things here?
Yes, the spatial hypergraphs are usually analogs of space-like hypersurfaces, right?
Yes, that's correct.
Okay, yeah.
Whereas these things, I'm not sure what these are. These are reconstructed. I mean, they're also like space-like hypersurfaces, but they're kind of a reconstructed thing. Okay, so I mean, I agree that the there's this versus versus this. So there's
Yes. The main thing on networks is that they are abstracted from geometry. They have only topology. And the question is,
they don't have topology. They don't even have topology. These ones don't have topology.
I mean topology, just the connections, not the general kind of topology of open sets. So the question is how we can reintroduce geometry in graph-like objects.
I know. That's yes.
Yes, and then the natural or first attempt that this is usually done is something I wrote in the comments as well, is to find the manifold embedding.
I know, but that's not what we want to do. Right? That's not what we want to do.
Because we cannot.
Right. That's not what we want to do, because we don't have a manifold, because we're not in an integer number of dimensions of space.
Okay.
Okay. There is no manifold embedding. If we knew what the manifold embedding was, we would have solved the problem.
These are intrinsic objects. So we are looking for some intrinsic geometry, not something that is extrinsic to an ambient space.
Okay. So that's, I mean, this is, Right. There's a whole long description of that in this whole giant section about limiting behavior in emergent geometry. That is a solid 100 pages of stuff.
For now, it doesn't matter whether we are talking about branchial graphs or we are talking about the whole space-time structure in blue. For us right now, these are just hypergraphs, and we can start thinking about what kind of geometry or calculus to define on them. Then we can worry about specifying to the case that something is a true space-time or space-like or whatever. That is
let's try to set the original. Okay, before we there's a definite path. The beginning of this path we know. So let's try and clarify the beginning of the path, which we know. Then there's later parts of the path that we don't know, which is why we're doing this discussion. Okay, but so okay, first question is, what are the objects we're looking at? Okay, the first thing that I think we should do is look at these spatial hypergraphs obtained by these sort of standard update orders. Am I making sense? Do people understand what I mean by that?
Mm-hmm.
Yes.
Right?
Yes.
Okay, so a limit of this object. Okay, now that object we know has an effective dimension that's not an integer, which is where okay, so there is no manifold, right? Manifolds are locally like Euclidean space. These things are not locally like Euclidean space, right?
Yes.
We don't know what, so this is exactly what this section is about, is there a model space? Euclidean space is a model space, which is kind of the local version of what a structure is like, oh, it's just like Euclidean space, okay? This is not that. Actually, question for people, in the case where we're looking at, for example, branchial graphs and so on, and where we imagine that there's ultimately a Hilbert space, what is the analogous local model in a Hilbert space? Can somebody comment on that?
What do you mean by analogous local model of Hilbert space?
What I mean is, maybe this is a silly question, but a thing that is a manifold, its local model is Euclidean space. So my question is, in a Hilbert space, what is the analogous local model kind of object? Or is that a silly question?
Well, I mean, it's a little tricky. I mean, depends on the type of Hilbert space. If one is looking at Hilbert spaces of square integrable functions, locally one can still define manifold-like structure on that by thinking of the open sets as they're part of some function space, but they could still be some maps to the usual geometries.
Okay.
I think what you're asking is what might be the generalizations of manifolds, still of continuous structures, but which are not necessarily completely manifold-like. So one obvious and straightforward generalization of a manifold would be an algebraic variety, where you can allow for there being singular points, and these are in fact spaces which are solutions of algebraic equations.
Right. So, for example, that tropical algebra case is a simple-minded case of that.
Yeah, that would be one example. But you can have all kinds of things, right? For example, you can in one dimensions. For instance, if you write a cubic polynomial, if I'm not mistaken, it corresponds to a curve where there's one crossing. That crossing, the whole thing is continuous, but at that crossing, the usual notion of differentiability is not defined. Or in a two-dimensional case, you can have a conical point. That would be so. This would not be a manifold because there is some local
but only at one point.
Yeah.
Whereas what we've got is something which is uniformly not a manifold.
Right. But I think one has to let's understand this object that we are dealing with first. There are of course differences. It's different from manifolds, but let's compare it to what's its real difference with this structure that you have where you discretize an actual disk. Now, in that discretization of the disk, the way we do calculus, there are many ways to think of calculus on that disk. One way to think about it is that, well, this discretization corresponds to simplices, and these simplices have some specific rules of definition and gluing rules, and in some continuum limit, those will give you all the usual constructs of measures and differential forms and other things.
Yep.
Now, in our object, which we should maybe think of a good name for it, what we actually have, in a sense, they are of course not simplices, but it naively, so of course it's true that there's no global dimension, but this dimension is a little subtle over here. If we think of our object as something that is some composition or some gluing of different hyperedges, of different arities even, then the main difference between the disk and this one is that in the disk, all the hyperedges are of the same arity. So if your disk was triangulated, all the hyperedges are of 2 dimensions. Whereas here, each hyperedge itself has a dimension. It's not that a hyperedge doesn't have a dimension, but you have hyperedges of different dimensions gluing the structure. So even though in our object, we don't have a global dimension, locally there is a dimension.
Well, I don't know what kind of dimension that is. I mean, look, we can think of this if we want to. We can make some dual graph here, dual hypergraph here. Is that what you're imagining, where every triangle has certain neighbors and so on?
No, I'm just talking about the hyperedge itself.
What hyperedge? Where's the? I don't see any hyperedge here. What hyperedge are you talking about?
No. One minute. I mean, how first? Okay, maybe let's clarify this thing first. How should we think of hyperedges in this context? We can think of hyperedges as if we have, for example, 3 nodes. We can think of that as being represented by a triangle. So we can think of hyperedges as not exactly a simplex. It should be something more general than that, but an object like that, which is either a triangle or a tetrahedron if there are 4 edges.
Right. That's exactly what I'm saying. I'm saying take every triangle here, treat it as a hyperedge. That's what you're talking about, yes?
Yeah.
Okay.
Yeah, and now all I'm saying is that if you do that same process in our object on top, locally, there are hyperedges everywhere, and each hyperedge you could think of as having some dimension, but it's only that as you jump from one hyperedge to another, the local dimension changes.
Fine. I mean, fine. I don't think that's that useful, but I mean, fine. Yeah. Look, I suspect some of these things have a certain degree of homogeneity in the limit. I think looked at in the right way, this thing will be homogeneous in the limit. Well, it might not look homogeneous when it's rendered in 2D or whatever, but I think it is homogeneous in the limit.
Okay, so I'm not complaining about it being homogeneous. All I'm saying is that our object is some kind of composition of a class of hyperedges, which if you think about it separately, okay, let's think about it this way. Maybe this is a better way to say it. If we decompose our object into sub-hypergraphs with only fixed arity in each case. So we take all the 2 all the 2 hyperedges, the 3 hyperedges.
Yeah, I understand. And this is a graph. So this particular one is a graph. So every hyperedge is just an ordinary graph edge.
Yeah, in this case, true. But what I'm saying is, if you think of this as a composition of each of those, then once you separate them, each of those will in the limit go to some nice manifold of standard algebraic variety. But what this means is that our object in the continuum limit is a composition of all these algebraic varieties of different dimensions.
I don't think this is a useful way to think about it, because I think that's, I mean, maybe, I think, look, I think there's some very obvious things to do, okay? I think what you're doing is you're trying to construct something where you're puffing this out into a thing where even at the lowest level, it has geometrical structure. I don't think it does have geometrical structure at the lowest level. I think it has emergent geometrical structure on a large scale, but not at the lowest level. It's like I could take Euclidean space and I could say, let me, go down until I get to the points in Euclidean space, which it doesn't have, and then go up from there. I think it's better to, I mean, that's really the question. Is this making any sense?
However, may I add something Stephen, because we had a similar discussion with Tobias, and it would be very helpful if he could join us. Because, for example, we were discussing about how one could go and have calculus on fractals, and he was working on something like this.
I know, but that's a different thing. There's a big literature on that. It's mostly utterly 100% irrelevant. Okay? There's a big literature where people missed the point. Okay? I have looked at this literature. I believe it has 100% missed the point. Okay? And what those people are doing is they're saying, we've got a two-dimensional thing. We've got a Sierpinski gasket in two-dimensional space.
Yes.
Now let's go and do things. Okay, that's irrelevant. Okay? This is an intrinsic object that has an intrinsic dimension that we can compute by looking at, we started a node, we build some GDC ball and so on.
Yes.
Okay? And it's not, it's
and
really not
are
relevant.
Not transferable. Okay.
It's really not relevant. I mean, I spent probably a week when we were working on the physics project originally, looking at that. I was extremely disappointed with what I found, which was nobody had figured out anything. I mean, they might have done, but they didn't. The people who come closest to figuring out stuff about this are people doing geometric group theory. They are by far the closest, and they have figured out some interesting things. Some of which, I originally interacted with those guys back in the early 1990s, and that's what caused me, and I think maybe even them, to figure out some stuff about how dimension works and so on. Okay, so so let's go back to where I think can actually get started, because there is no magic bullet here. This is not understood. There is no literature. It's, we're starting from scratch. And, unless there's some amazing thing that I've never found, but I don't think so. Okay. And no method like manifold reconstruction, all these things, none of these methods will do anything, basically. This is a from scratch enterprise, I believe. Right.
What is the major difference, Stephen? You would say, because between the structures they are working on and what
they have an embedding space. We don't have an embedding space. Everything we have is represented by this object. It is all intrinsic. There is no embedding space.
But we can construct an embedding space in the
No, we
limit as
can't.
well.
No, we can't. If we construct an embedding space, we lost the game.
It's too abstract. It misses all the structure.
No, there is no embedding space, because embedding spaces that people look at are ultimately Euclidean, finite, integer dimensional spaces. We don't have that, and we don't want that, and that's not what we're doing. And as soon as we do that, we've lost the game, because we can no longer, what we're trying to do is generalize away from what people have done for the last 300 years in, integer dimensional spaces. Okay, and the generalization that the fractal people have made is, the geometric version of that is not what we need, right? So let's go to what we actually can, I think, do, and what okay, and which is plenty. So let's start off imagining we have an object like this, and I already made a list of some of the most basic things here, like what is a point, right? Presumably a point is a node in the graph, right? So if we're trying to build geometry, what can we build? Do you understand what I'm saying?
Mm-hmm.
Yes.
Okay. So, and what I want to do is, so for example, a point, right, is, point is a node in the graph. So let's draw on our base. Actually, I want to make a smaller base object. Let me just make a, I don't know what size of base object we should use, but let's say base obj 10. Let's just do the size 10 version. Okay. Maybe we should pick a different one of these. Do you like this one? Anybody got an opinion?
This one's chaotic enough. For the definition for orthogonality of lines, that's only local, right? As soon as curvature comes in, that one fails.
I'm sorry, what are you saying?
So on the right, you have that definition.
Wait. We're not looking at the right yet. We're just looking at the left.
All right.
Okay, and I'm asking the question. We're going to use some particular rule as our example rule. Okay, can we think of a better one than this? Do we know? Have we looked at ones? Does anybody have an obvious favorite that's better than this? Maybe I should look at what I did here.
Maybe take one that is hairy and not completely regular, because there will be all sorts of subtleties in the way these continuum limits have to be taken.
I know, but we want one. We're just going to take one. Look, we want one. Those aren't very good. Does this have all-time favorite rule? Maybe we should just take that all-time favorite rule, not one that does something like this. Okay, I like that one. All right, let's try taking the 11-step version of that. All right. I mean, you know, it can be anything, but let's just take this. Okay, so now what we want to say is highlight graph of base obj 11, and let's say just randomly, let's pick node 50, and let's does anybody know how to style what is it called? Is it called highlight style? Anybody know how this works?
What do you want to do?
I want to make a big red dot.
I think it's vertex size.
No, I don't think that's, you mean in the highlight graph?
Yes.
I think you just include the style as the field argument.
Okay, what
Like
about
red.
if I want? Yeah, I understand, but what if I want no.
Okay.
Okay, there we go. Finally we got, okay, that is a point in our space. Okay, so now let's imagine we make a line. Okay, how do we make a line? A line is presumably a shortest path between 2 points, of which may not be unique. Okay, so here, let's just make that explicitly. Who knows how to do that? We would say here, let's see, we want, in this, we would want to say the highlight, can somebody help me here? Is find shortest path.
Yeah, I think there's find paths or something like that, that does all of them.
Although this should be geodesic, I think any path should be considered a line.
No. Yes, I know that. I'm simply trying to find a path, right? In this graph, right? Okay, so let's say we go from 50 to 100, for example, here. And that would be, so let's just see what find shortest path does there. That should be, oh, wow. Oh, you know what? I made a mistake here. What I should do here is to say undirected edge.
Yeah.
Okay, so let's say, okay, great. Okay, so there is our path. Now, it may not be the only path. So let's see, is there a way to get, what is this doing? How do I get multiple paths? Gives
I think that's
a
find
path.
paths. If I remember
Find
correctly.
path. Okay. Path of length at most k. But how do I want the shortest path? But what
so
happens if there are multiple
if-
shortest? Oh, I see. I look at the length of this path, and
Yes,
then
you
I
make
use
that case
find
with-
path. Right. I mean, my goal. Okay, this is my meta approach here. I want to make a bunch of definitions, and every time we make a definition, I want to actually implement the definition, because I think what we're going to discover is that some of these definitions aren't quite as simple as we thought they were. Okay, and let me make a general comment. Okay, I think we're going to have a bunch of definitions that apply to any hypergraph, okay? Even a finite, finite hypergraph. And then there will be limiting definitions that apply to this object, we might call it a hyperfold, that is this limiting object whose nature we don't understand very well yet. And what is a hyperfold? A hyperfold is some kind of limit of rules being applied to a hypergraph. It isn't just an arbitrary infinite hypergraph, because that's an unbelievably messy object. I'm making sense?
Mm-hmm.
It's an object whose nature we don't understand very well yet. It is an object in the world of, okay, so let's actually, what is a hyperfold? I'm not sure that's a great name, but let's call it that for now. Okay, so it is a limiting object, and analogy, fractals / nested structures are also limiting objects from applying nesting rules, right? Limiting objects from neighbor-independent substitution systems. You see what I'm saying?
Yes.
You
And I
you
think,
can also specify.
I think
So-
random graphs also are good examples of limiting objects from which we can draw some techniques and definitions.
I don't think they're as useful as you think. Okay, and let me explain. I mean, graphs that have been constructed using some kind of preferential attachment thing or some such other, growing. Okay, there is random graphs with grown with an algorithm.
One kind, yes.
Well, that's the kind we're talking about, because by the time it's a random graph, you kind of lost the game. You're not going to be able to say anything.
Yes.
I mean, there are things that can be said about random graphs, but they're
Some
not
things,
the type
yes.
that we're interested in.
Exactly.
Okay, but the thing that's interesting here is a typical fractal that you get by doing so. So, for instance, we should be able to get. I wonder whether we have an example of this. I bet I have an example in here. Do I have an example here? Sure, I have an example here. Well, one of these things.
I mean, maybe we could use their language, not the tools themselves.
No, just a second. So one case is, we can make some kind of Sapinski-like thing out of, I'm sure I had one of these actually. I'm sure I had one someplace here. That's a tree, but where is the Sapinski-like object? Maybe I didn't have it here, but I have it. Let me show you.
So you can specify some properties of this hyperfold, and especially what do we expect? What type of things do we expect it to go to in the continuum limit?
Yes.
It could be more than one thing. So one obvious continuum limit could be just the usual algebraic variety. Another continuum limit could be a completely different thing, which is more fractal-like structure. So there could be different types of objects one expects from this hyperfold in the continuum limit, not just one thing.
Perhaps. I mean, look, here's an example of a very straightforward, substitution system that gives us something that is a sort of traditional fractal object.
Right.
Makes sense? Okay, so what we're seeing is a different kind of limiting object that does not have this neighbor independence property. And that's, in a sense, what we're, in the case of the spatial hypergraphs, we are effectively building something which is like a neighbor-dependent substitution system, except that those things have this whole multi-computational feature. They can't be you can't just say, take every position and update it. There's this complicated ordering dependence. Does that make sense to people? I mean, that's why we have to pick these complicated foliations and so on.
Meaning that if we apply the same rules in different order, we get a different object.
Yes, that's what happens. That's what happens. And that's what happens, that's the whole point. In a thing like this, that's what these multi-way graphs are all about. This is the result of a particular path, a particular evaluation order using the rules that we're using will give this. A different evaluation order will give something different. And the whole point is with causal invariance, we can make all sorts of statements about equivalence, blah, 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 blah. But the point is that the limiting object on some particular kind of fiber going through the multi-way system, you know, that's what we're trying to discuss, is what is the calculus on that limiting object, which is not unique. It, you know, a different fiber would give an object different in detail.
Yes.
Just as in the case of something like this, a different triangulation, we might have different detailed triangulations, but nevertheless, the Euclidean space limit is the same.
So we could say that we're looking at a collection of things and we're trying to see if we can define some kind of continuity in the collection of things, where maybe a point would be a limit of a particular history.
I'm not sure that's right. I'm not sure that's right. I think that my feeling is the right way to look at this is to look at a single object in the limit, right? Looking at the collection of objects is a different activity that may be necessary to, my prediction is that there will be a whole bunch of properties that we can define on any hypergraph, okay? Like a point, a line. I mean, I've got this list over here, wherever it was, of things that people are already objecting to, but we'll get to these, okay? The, you know, there are things we can define that work for any hypergraph. They only are nice and clean in the limit of a very large hypergraph. Then there are things which will only be definable. Infinitesimal calculus will only be definable on an infinite hyperfold, or an infinitely fine hyperfold. That would be my expectation. We can get finite difference calculus on a, you know, a non-infinitely iterated hyperfold. But a hyperfold will be the limiting object that we don't yet understand and that we're trying to get towards. But I think the way to approach that is to look at the, you know, look at things that we can define on any old random hypergraph.
As a matter of fact, the finite different approach has been applied already to contagion and
I know in
processes.
graphs.
So,
yes, I know that. Exactly. I know that. There are about 3 things you can do with it, and they're mostly running the Laplace operator.
Exactly, the Laplace operator, exactly.
Yes, I know. We will get to that. We can run the Laplace operator. We can do some level of discrete harmonic analysis on these things.
Yes.
Let's go. Let's start off. We're going to have a point, a line. We're going to channel Euclid here, okay? Because, you know, okay, so here, let's look at our line where we said there's a shortest path here. Let's find the length of that shortest path. By the way, that's a distance, right? That concept of the length of the shortest path would be a distance somewhat inadequately. I mean, let's just write that down because I believe that is a thing, is distance between points, which presumably is what distance should always be thought of, is the length of the shortest path. Do people agree?
Yes.
Yes, this just specifies the path metric space in general.
Indeed. So let's also make a note of that, because this is what we need to make this a path metric space. Right? And that, so what we need to make this a path metric space, we need points and distances, correct? Do we need anything else?
Also, a path metric space, the way that there's some requirement on the distances, where the distance is the length of the shortest path. And since we have discrete structures, it's basically just the sum of all the points on that path, the length between them. Because it is possible to define metrics that aren't path metrics.
Okay, so let me understand that for a second. So you're saying, assume, this, we are implicitly assuming that the distance between any 2 points, distance between adjacent points is 1 unit. I think that's one of the issues here.
Yeah, so that directly specifies, if you do that with the path metric space, then you directly specify the graph metric.
That's the metric we're getting, yes.
yes, we can go slightly more general by not assuming that. And that's one thing, and just assuming it's a path metric. But I think that's fine for now. Whatever we end up with will probably be generalizable to path metric spaces in general.
Right. But so what I think is going to happen is we're going to get some things that are true for hypergraphs in general. We're then going to want to define functions on hypergraphs, which is where we'll get Laplace equations and other such things, and where we will also get, in defining functions on these graphs, one thing we can do is paint a value at every node. We can also paint a value on every edge. And so the value we paint on every edge could be a different assumption about the distance on that edge. And again, I don't know what is consistent, right, in doing that. And we'll have a notion of continuity, which hopefully we'll get to. Does that make sense to people? I mean, that will be, but let's go back here. We've got find path, and we will say here, let's see, the way this find path worked, we've got between 50 and 100, and we say, I want specifically paths of length 11, and I want infinity number of paths. Well, let's just say 5 paths. What the heck? Are they the same? No, they're not the same. Okay, let's see 10 paths. Oh my gosh. Wowee. Really?
Since
wait. Are they all different?
It will probably be different in like one place, so they choose to go left and right on different places, and then kind of exponentially.
So I wonder, do we have the nerve to type infinity here? Let's try that. Oh.
Oh.
Okay, so this is the length of this. Okay. All right, so we've got 100 of those. So now I want to show those as highlighted paths, right? So how do I do that? I've got those paths.
You can do path graph / at that find path, and then that should do it.
And are they going to be red or something? Who knows?
They should be different colors.
Okay, let's make this graph 3D just so that we can rotate it around and see the thing. It's very inconvenient. This thing was right at the ridge at the top of our creature here. Okay, so the first thing that's happened here is that a line is not a well-defined object because we can have multiple GD6 here, which is not problematic, except that takes us away from Euclid, obviously. And okay, all right. So, but then we've got this notion of a line, and we got the notion of distance between points. Okay, what's next? Do we want the notion of a ball, or do we want something else? We could look at a triangle.
We could see it as a class, Stephen, and see it as a flow. So the whole class could be a line instead of its individual path.
Fine. Okay, well, shortest path, well, okay. Or
what's been useful for me in this case is the concept of path deviation, which is basically just asking how far do these paths actually go from each other, because that helps us differentiate between like this, which is basically the class and it's one line between, and for example, on a sphere, when you have from the pole to the pole, you have completely divergent paths that are different lines. We can kind of feel fundamentally, even though they all go between the same points.
Right. Something I just did yesterday. We now have data on flight paths. It's kind of amusing. We have data on all these airplanes flying across the US and things. And so I was looking at the geodesic bundle, except it isn't geodesics, of flights between New York and LA, like yesterday or something. And it's kind of interesting because it is so not, what am I saying? It's a bundle like this, right? As a result of the wind and God knows what else. Okay. Well, so what are you saying? You're saying okay, so another concept here is what? geodesic, what are you calling it? The thing.
And the path deviation.
What do you mean by that?
So if we look, for example, on each of these paths, we have a set of points that are distance 1 from the starting point, distance 2 and such. And then if we look at each of those, what is the in that set of vertices, what's the farthest that they're ever from each other? And then take the
I
maximum from that. That rigorously tells us how far these paths deviate from each other.
Okay, that's a
And
good
then
idea.
If that's large relatively to the length of the path, then we know it's probably different paths.
Well, I mean, that path deviation, that's sort of a test for, this is a test for whether it is really one path.
Yes. Yes, you specify some cutoff.
Okay, but I think that's not an immediate concept. I mean, I agree that's an interesting concept. I think
Yes,
there are
that's
more
just something
basic
to have in the
concepts.
back of the mind.
Right. I mean,
can we alternatively define?
Go ahead.
Can we alternatively define it like the distance as number of the shortest path between 2 points? Does it make sense?
The number of shortest paths.
Yeah.
I don't know what the number of shortest paths means.
But see, that's ill-defined, because if you have certain chaotic paths, they can be quite close, but if you have every point, you can choose left or right, and then they converge again. They get exponentially many paths with the length of it, even though they stay close together. While you can have only 2 paths, but they go
Right.
completely different side of the graph, and we want those
So,
to be
I
different.
mean, I
paths,
think what
even though
Jean
they're
is
2.
saying is what survives in the limit. And in other words, i.e., in the limit, is it one path or several?
Yes, it was an attempt to define injectivity radius on these structures.
What does that mean?
So injectivity radius is when there's an injective function between your tangent space and your geodesics. So for example, your injectivity radius on a sphere, this example is just as soon as you are on the opposite poles, you have infinitely many paths. So you don't have an injective function between your paths and kind of your tangent space, because if you have a tangent space, you get a path and then it goes to a point. But if you have another vector in that tangent space, you can get to the same point. Is the idea behind that. But below that radius, you can always have a unique correspondence by if you take the exponential map of this vector, you get to this point and you can go back again. So on these graph objects, if you have a particularly chaotic one, the interesting thing is that you also get a minimum radius, which is something you don't get on a manifold.
Right.
Yeah.
Okay, so I mean, we've also got concepts like tangent space, but I think that's a way further down the line concept. I mean, I think a tangent space, that is a limiting concept, isn't it? I mean, that is going to be, right? So that's so let's do things which are not limiting concepts first. Okay, so I mean, path deviation we can certainly work out, but let's look. Okay, so a ball is, I think, a very well-defined object. Do you agree?
A geodesic ball, right?
A geodesic ball.
As soon as you have a metric, yes.
Okay, so let's just make a geodesic ball because we're making things here. So the geodesic ball would be, how do we do that? We want a neighborhood graph of node, which one was our favorite node? Node 50. Is that right? We want the geodesic ball is the neighborhood graph in base obj 11 of node 50, let's say 4 steps. Okay, so that is our rather ugly looking ball. Actually, I don't even know. That's not really the ball. That's just telling us what points are in the ball, right? Is that correct?
Yes, and the border is the sphere, let's say.
No. I'm trying to understand. Is this okay? So that is our analog of a sphere for this object. No, it's an analog of a ball. It's not a sphere. A sphere will be the surface, right? Do people agree that is our geodesic ball? Yes, of a radius 4.
Yes, I agree.
Okay, so now the next thing we can say, we could define a geodesic sphere, which is the surface of that. Do you agree?
Yes.
Yes. So to subset of this and 4.
So the way we would do that, say that again, I'm sorry.
So it's basically just all of them in the neighborhood graph that are exactly distance 4 from the origin.
Mhm.
Yes. How do we do that? Is there a way of doing that?
For
in
now, it's
neighborhood
just a
graph?
set.
Oh, wait. Is that well defined? And is there a way of doing that with neighborhood graph? Is it well defined to say exactly distance 4?
Yes, that should be
Yes,
well
it is
defined.
defined. Yeah.
Yes.
So the easiest way I've been doing it is just basically taking neighborhood graph of distance 4 and then taking away the elements that are in neighborhood graph distance 3.
Okay.
It's probably a better way, but it works for small examples.
Okay. So can we do that by vertex delete, or what do we do?
And that should work. Otherwise, vertex list of both and then complement or something, if I remember correctly.
Right. But if we do, deletes a collection of vertices. Okay. So if we say vertex delete here of neighborhood graph of this, comma, vertex list of this. Do you agree? Oops, 3 there. Okay, so then this is our sphere, which somewhat confusingly is not connected anymore.
Yeah.
There are many isolated points there.
One idea would be to get also all the minimum distances between these, the geodesics between these points, but then it might not still be a sphere of radius 4.
Right, that's a different
Yeah.
thing. But what's interesting here is the sphere is not necessarily connected.
Mhm.
Is that true, guys?
Yeah.
In general, that would be, but I think we could expect that to not be the case if you take the limit.
Okay, so at least for finite cases, the sphere may not be connected. Whereas the ball is connected by definition because it's connected to the center point.
Mhm.
Right? Okay, so now next thing I want to do, I was thinking we could define a triangle.
We could also give the number, the concept of volume by counting the number of nodes
Yes, that's
inside
correct.
the ball.
That's correct. Let's write that down. So, well, is it any, wait a minute. The volume of, oh gosh, what is it? Is it the volume of anything we can get? No, that's not obvious. The volume of a ball.
I would be skeptical of that because it assumes homogeneity on all scales, which is not something we have necessarily.
Okay, but one
So-
thing that's interesting is it is not obvious given okay, so possibly a count of the number of distinct nodes. Actually, no, this is okay. This is a count of the number of distinct nodes in the ball. We've used this many times. Actually, it's not really the volume. It's really the quotes content of the GDC ball.
The concept of volume should also take into account the dimension. For example, the same number of
I know,
nodes
but
should
that's
be
exactly
volume.
But volume is a little trickier because usually before defining volume, one thinks of what's a measure, and then one looks at all these definitions of measure. We haven't gotten to that point yet. So claiming something to be a volume is a little tricky.
Okay, so possibly not yet. Okay. Not clear what the measure is, what the measure talks about.
That would be a definition of measure.
The only measure we have is if you're looking at those path metrics or graph metrics, then at least we have the measure of length over there. But besides that, we haven't yet specified any other types of measure.
I think this is, as Jean is saying, this is basically a definition of measure.
Mm-hmm.
But yeah, I think it's important to note that we can define something else possibly. There's no clear reason to get married to this specific definition.
Right, although it's a useful definition. And again, okay, so let's keep going. I want to try doing a triangle. Okay, so we can take, okay, so given 2 GD6 from a given point, right? Imagine But what's the next primitive notion? Is it an angle? Is it a triangle? Is it orthogonality? What is it? I think it's a triangle. Can we define a triangle? Okay, so a triangle would be given 3 points ABC, draw the GD6 between them. Is that correct?
In a sense, what you mean is loops, right? Once you have geodesics, you can ask what's a closed geodesic, and those are loops.
Yes,
And-
that's right.
And a triangle is a special case of a loop. You
Right,
can have all kinds
exactly.
of loops.
But
Okay,
we
but
can also
let's-
have degenerate cases where, for example, 3 points form
Are
the triangle
collinear.
as well.
Yes.
Yes, exactly.
Okay, but let's look at the triangle, because we can then ask, a lot of differential geometry is done in terms of triangles and so on. So let's make a triangle here. So for that, what we want to do, oh boy, this is complicated again. This is complicated because we don't have a unique path, right?
Yes.
Okay, so the points do not define, okay, hold on. Perhaps it is not true that 3 points define a triangle.
Yes, so this is where my necessity of the path deviation definition comes in, because if you limit path deviation to some degree, then you get a certain level of accuracy almost defined that is defined by 3 points. If you choose 3 points, you get some accuracy to a triangle if you have some bound on the path deviation of each of the 3 edges.
Okay.
So that might be useful in this case, actually.
Okay, so hold on. It is not true that 3 points necessarily define a unique triangle, because there may be multiple geodesic paths between the points. So is that even true on the Earth? Do 3 points define a unique triangle, or is there one that goes around them?
As long as 2 aren't antipodal.
Okay,
So
so
it's once again the injectivity radius.
on a sphere, 3 points do define a unique triangle, except when 2 of the points are antipodal. Is that correct?
Yes. So if you have that your 3 points aren't mutually in each other's injectivity radii, then it doesn't uniquely define a triangle.
Okay, so I think I'm going to have to understand this injectivity radius. So, so the concept is, let's go back to, we didn't define it here. Okay, so basically you could say, I'm running out of levels here, injectivity radius. So essentially that's the roughly
Think of the example of a cylinder. Okay, you have 3 points, and there are 2 ways you can draw a triangle, right? The base can come from one side or the other. And that example would extend to saddles and many things, including the sphere.
Okay, hold on. So roughly, this is saying this radius is how far apart can 2 GD6 get?
No, how far apart can 2 points get? And there's a unique geodesic between the shortest geodesic between them.
I see. Okay. That's the definition. How far apart can 2 points get while still having a unique geodesic? Okay, let's compute it for our puppy here. Okay, so clearly it's going to vary with position, on this object?
Yes, on manifolds in general, it does as well.
Okay. In general, will vary with position. Okay, so let's see, for that position there, for the position for the 50 point, let's try and work out what it is. Okay. So what we're going to ask is, for a given, how can we compute this?
And so without the path deviation, it's going to be extremely short, because as soon as there's two ways that are equivalent, it's going to start deviating. So I would expect it to be like 2 or 3 in general for any point in these types of structures.
Okay, well, let's figure it out. But then you can have, I mean, okay, so then there's a, presumably there's a, consider also a fuzzy injectivity radius of some kind, where the geodesic doesn't have to be unique. Isn't unique, but at least doesn't get too far apart.
I'll quickly grab my code for the path deviation, maybe. Let me see.
Yeah. We can write this. But we should be able to color the whole, hypergraph by how big the well, okay, so maybe we should go back here. What is the, okay, the path deviation could be, is this in fact, okay, so wait a minute. One thing we could do here is going along all geodesics between 2 points. What is the maximum distance, geodesic distance between any 2 corresponding points? Is that right? Is that
Yes, that should be. I posted what I think was the functions in the chat.
Oh boy. Okay. All right. We can look at this. But I think hold on. Hold on. Let's. I think we got a simple-minded way to do this. Okay. So we've got here. This is the collection of paths. Okay. So that gives us. There's our collection of paths. Now, what we want to do is transpose this, if I'm not mistaken.
Yes, and then delete duplicates.
Okay.
So this works for short paths, definitely. Mine is optimized for longer paths, so it's not necessary at this stage.
Okay. All right. Okay. So that's those. Okay. So that's the transpose. And now some of those have length, obviously at the endpoints, it's length 0, right?
Yes, it will always be.
Okay. So now if we say delete duplicates onto each of these, actually, we might as well say union. Okay, so now for those, we need to know how puffed out is this thing here. So is there a graph distance?
There's some sense of graph distance matrix that works on this, if I remember correctly.
Yes, I would think so. But graph distance, okay, so this is the max. This is, look, we could compute this as, okay, so we could do outer graph distance. This isn't the most efficient way to do it, of base obj 11 on, let's just pick a pair of them. Well, let's just do this. Okay. So #1, #2. What the heck? No, don't crash. Oh, what is that? Why is that wrong? Source to target in graph G. I don't
Doesn't outer
understand.
need two lists?
Oh, look, S and T, source vertex to target vertex in the graph G.
I think the problem is with outer. So I think outer needs two lists. So
Oh,
I think you need
silly
the
me.
list repeated.
Yes. Okay, there we go. All right, very boring. Now, what we could also do is to compute the graph distance matrix, but okay, but that, so here, well, that was very fast. So we can actually probably just do this. Okay, so then what we do is for each one of these, what we are doing is the outer onto okay. Okay, so those are our distance matrices, right? So then
Yes, it should
the
be.
deviation is given by the max of each of those.
It should just
Okay.
be the max of all of, yeah, it should just be max of the entire thing.
Well, I understand, but this gives us a finer grained thing. This is the thickness of that geodesic cable, so to speak,
Yes, at each point, yes.
right?
So,
Which is
so I
itself
usually
kind of
took the max
interesting.
of that.
Right. Okay. But so this is but this is a more differential path deviation. What is that concept? What that concept is, see, then we could imagine segregating these geodesics, right? Because we could say let's imagine that here, these are rather small numbers because they're sort of all going around the same side. But if some of them were going around the opposite side of the Earth, if I'm making sense, then, we could imagine some kind of, clustering / segregation, but this is where things are going to get of different geodesics, if that makes sense. So it's like which one trying to see which ones will be distinct in the limit, in the hyperfold
Yes.
limit, so to speak.
So this won't be defined in general, though. So if you think of a sphere, but in most cases, most practical cases, it should be quite a useful thing to be able to answer. I agree.
Yes. Okay, let's go back down now. So this path deviation is sort of an indicator for, I don't like having to use this, okay? So in other words, as far as I'm concerned, I'd like to know, because one of the things we need to understand is what is the hierarchy of definitions depending on? See what I'm saying? And by the time we say, oh, well, you got to have a path deviation less than some number, this is like, the thing is we want definitions that don't say epsilon is equal to 0.7 or something. If you understand what I'm saying, it will be nice to see which definitions don't depend on a kind of semi-arbitrary cutoffs and so on.
Yes. So if we work on limits, and then so what I usually did is I took that and I divided it by the length of the path. So we would expect in the limit for paths that are the same for that to go to 0, and for it to stay finite for distinct paths.
Yes.
So then if you're taking the limit, you don't need an arbitrary cutoff. But if you're not taking the limit, then an arbitrary cutoff is necessary.
Right. So one question is, what concepts can we define without arbitrary cutoffs?
Don't these cutoffs, in a sense, have some resemblance to some generalized notion of being antipodal?
Okay, that's an interesting question. Okay, so let's ask that question. Okay, so let's ask antipodes, and I think Nick was asking here about symmetry. But let's see, are antipodes a generalizable concept? Yes, I think the answer is yes, right? An antipode is what point, is that generalizable? Let's think. What point, we're asking, okay, an antipode, okay. Yeah, what point is furthest from a given point? I think that means something, doesn't it?
So don't we want, so for coming back to the cylinder example, we kind of want for any point, wouldn't the intuition be the entire strip on the opposite side is antipodal to it? Or am I misunderstanding what
I
they mean by
agree.
this?
What points are
So it's not, furthest isn't necessarily the word, but it captures the intuition at this stage.
Yeah, it,
Well, let's
it doesn't have to
see.
be a point. It can be a more general structure, but an antipode is usually defined in terms of some symmetry. And here, even if we don't have a concept of symmetry, these antipodes seem to be some notions which are generalizing this thing about thresholds. And in a way, this should be a kind of operational way to speak about when something is past the threshold or not.
Well, let's okay, so hold on a second. Let me just I think we had a graph antipode function. Yes, here we go. Conveniently, we have a graph antipodes function. Oh, why didn't that work?
So would one way of thinking of it be, so if we do take, so the geodesic deviation divided by path length, if we think of, for some point, we have a scalar function, which is basically what is that the path deviation to that point. And so that scalar function will be, in a sense, discontinuous at the antipodes, right? Because in the limit, it's going to go from 0 to some finite value. So for finite cases, it should meet some criteria for being a discontinuous scalar function.
Okay, hold on. What you're saying is we're already then talking about functions. I mean, that's another section basically, is functions on the hypergraph. And one type of function, one function
is a very naive version,
is distance, e.g. Okay, so it's basically paint a scalar value at every node. Okay, so one instance of that, e.g., put the geodesic distance, put the distance from a given node as the value at each node. Right? Can we let's just look at this? Okay, resource function. Let me just do this. This is highlight graph of base obj 11. Okay, so this will claim to make, oops, no, that doesn't make any sense. Oh, a pair of vertices which have the greatest distance between them. How do we do this graph highlight? What do we do for the style here? I've forgotten again.
Vertex size 10 worked last time.
Okay. It was 1. Is it 1 or 10? Maybe it's 10. Was it 10? Huh. Okay, so there we have 2 antipodal points, but I don't understand why there aren't like gazillions of antipodal points.
So I think what this is doing is it's computing the graph diameter and just seeing what pair of points are distance graph diameter from each other. Would be my guess, which is not what we mean at this stage.
No, it is not. It is not. I mean, so this one, this attempts to find.
For us, it is always with respect to a point, right? You say that given a point, is there an antipode?
Right. Okay. What we want the antipode of a given point. Okay, so how do we find that? What we want to do is we want to find the graph distance matrix, if I'm not mistaken. Oh, actually, if we do this, hold on. I wonder if graph distance has a way to do this. Yeah, distance from S to all vertices of the graph G. Okay, so if we go base obj 11, what was our favorite point? 50? Okay, there we go. Okay, so those are the distances to every other point. Okay, so actually we could just look at a histogram of those. Okay, so now what we want to do, the antipode, is the point which is the maximum graph distance away. So we want to find the, how do you find that? Let's see. This is rather grotesque. Position in U of max of U, correct? Oh boy, look at that. Okay, so those are all the antipodal points to our friendly point. Oh, no, those aren't the points. Sorry, those are the positions. So now if to get what I want to do is I want to say vertex list. Oops. Vertex list of base obj 11 of this. Am I right? Okay, so let's see what that looks like as. Okay, so this claims to be the antipodal points. And then anybody know how to style? We want those, and we also want the original point, I think. So how do we style these differently? Any ideas?
So we can do vertex style goes to, and then a list of just
right.
colors.
Fine. Okay, fine. Let's just do that. Okay, so let's say prepend to this, comma 50, and that was our thing there. And let's say vertex style.
Although I think that this could become could be achieved more easily, because what we're looking for is the eccentricity. So if we find the radius, the sphere corresponding to the eccentricity, which is the maximum distance from a particular point, we might be able to generate the same points
All right,
quicker.
see if you can figure that out. Okay, hold on. Let's just
Mhm.
do this for a second. So vertex style is prepend blue to table red length of P, if I'm not mistaken. Okay, well, apart from the fact that we want to probably say graph 3D of this, did I get that vertex style thing wrong? I don't understand that. We've got.
I think it should be correct. I'm also confused.
Okay, well, that's kind of cute to see the antipodes there, the antipodal points. I mean,
I think it should be the blue should be the second argument of prepend, shouldn't it?
Oh my gosh, silly me.
Again, now I'm just confused.
So am I. Well, let's try making it green instead. No, help. You know what's happening
You can use style, just style and your vertex.
around the vertex.
Yeah, wrap style around your vertex, and it should work in highlight graph.
Okay, all right. So let's say style of hash comma red slash at P prepend that to style 50 comma green. Ta-da! Well done. Okay, cute. Okay, that's an antipode. Now, what do we learn from that? I'm not sure what we learn quite from that, except that what is the use of the antipodes?
This isn't quite what I meant by antipodes. It will correspond in many cases, but I'm basically, well, this might be the actual definition. I might have it wrong. But so on a sphere, this is the same. But so for the example, this cylinder, the maximum distance will just kind of be on the opposite side at the end of the cylinder instead of the entire strip down the middle, which is the intuition I've had behind that word.
In the case of brancher space, I know how to go from one point to the antipode in the Hilbert space of quantum state using the Wolfram model.
How?
Could I share the screen?
I think this is going to take us off topic.
Okay.
Is this on topic or not?
It is about generating effectively the Hilbert space in the Wolfram model as a limit, but I am in the substitution system. I am not using the hypergraph system, the substitution with characters.
Okay, way off topic.
Okay.
The interesting but way off topic. All right. Let's okay, I want to see whether we can get to triangles or whether triangles are a fraught concept. Okay, does anybody think, okay, so one way to get a triangle, the problem is there isn't one triangle, right? The triangle is going to be some whole, I mean, let's draw what our best approximation to a triangle, which may be good enough, right? It may be that a triangle has fuzzy edges in all cases. Am I making sense?
Yes, so the idea behind the path deviation is just to quantify how fuzzy those edges are.
Right.
It's my intuition behind it.
Right. No, I agree with you. But the question is it good enough? Can we start working out things about geometry with triangles, with fuzzy triangles, or is that not going to work? In other words, if we try and build things on top of triangles, so let's draw some triangles here, okay?
So my project on curvature is based on triangles, and so those have pretty convincing, well, encouraging results in terms of how well it works in cases where the path deviation is relatively low.
Cool. So your
the tolerance isn't even too low, but yeah.
Okay, so let's see if we understand some of that. So because generally, right, we can look at the area of a triangle based on its side lengths, right? And that gives us, that is some kind of Gaussian curvature, isn't it?
Well, so if you have both curvature and edge length, then you have area. Well, from those three, if you have two, you have the other one, but you need two of the three.
Right.
I try to stay away from area.
Okay, but I think there might be a way. Okay, here's a question. If we Nick is suggesting triangles wedge product between two paths. How do you get, what is a wedge product? So given two paths, what you're doing, you can look at all crisscrosses between those paths. Right? Given two paths, you can look at the outer product of every point that you can reach. Is that correct? Okay, so wait a minute. Okay, let's have a concept of which we might call webbing. Okay, webbed regions, which admittedly is a different concept than, it's not a traditional concept. And so a webbed region would be something, let's see, where do we pick here? Well, we had a nice distance. What were we picking? We were picking between 50 and 100, right? So a webbed region would be, sorry, just a second. So that is given 2 JD6. Actually, that's not even the next primitive concept. No, wait a minute. Oh gosh, what should we call this? What do you call it when you drop a perpendicular from a point to a line?
You mean the normal or what?
Yeah, but that's the normal. But what I'm thinking of, okay, given a point and a geodesic, and a geodesic not through that point. Find the webbed region formed by all geodesics from the point from the point to the given geodesic. Do you see what I'm saying?
You mean the light cone of a point such that the geodesic is its Cauchy surface, something like that?
Something like that, yes. But so what this is, let's just make one of these, okay? So we're going to pick the geodesic, okay, geodesic from 50 to 100, of which there are several. And point 150, let's say. Okay, so this is some kind of triangle. Maybe this is what Nick was getting at, more or less. Wait a minute, is this, wait a second. So we form all geodesics from 50 to 100. So let's figure out how we do that. Got a way of doing that here. Okay, let me write a function. It's called all geodesics between 2 points, right?
Mm-hmm.
So this would kind of make the definition fuzzy squared in some sense then, right? Because we're taking fuzzy lines between already fuzzy lines. Or is there another way of thinking of it?
No, I think that's basically right, but I want to try to understand what this is. Okay, so let's say all geodesics of a graph G and point P1 and point P2. Okay, and so what do we do here? First thing we find is with len equals length, the shortest path from G to P1 to P2. Okay. Now we want to find, oh gosh, that 100 is really arbitrary. And I'm upset by having to use that. And can somebody send in a complaint that find path should, maybe there's an all argument for find path. Let me just find out. Oh, there is. How nice. But it should support infinity as well. Could somebody send that in as a bug report? If no, I'll do it. Anybody here able to do that? Nope. Okay. It's on me then. Hold on. Okay, but anyway, we've got a way that works here. So find path all there. And I believe that's all we need. Oh, oops, not 11. That's with length len there. Do you agree?
That could be
Also, instead of 100, we could put a max eccentricity of G, so it's less
We don't
arbitrary.
need it. We don't need it. All works just fine.
Mm-hmm. Of course. I mean, in general.
len instead of length of find shortest path, shouldn't we just do graph distance?
Oh,
Isn't
yeah,
that
absolutely.
more efficient?
Yes, absolutely. That's nonsense. Okay. That's what it should have been earlier as well. Okay, so that's all geodesics. So let's just check that for Really? We had many more geodesics before. Right? Up here, I am confused. 50 to 100 of length. Okay, let's look at this. Graph distance. Okay, what's going on there?
So the find shortest path, so that's going to have the origin vertex as well. So it's going to be one more than the graph
Yeah,
distance.
exactly. So the correct answer here, rather confusingly, is +1.
Should it be, or was the other one wrong and it should have been -1? Because find path has the distance as the maximum distance, right? Or is it the maximum path length in terms of amount of vertices? Because if it works with graph distance,
Hold on. Let me think about this for a second. Okay, so what we're saying up here is,
so if the upper one works with 10 instead of 11, then it should be 10 instead.
okay, hold on. Find shortest path here is this. And the question is the path, that is the path length, right? That find path is finding paths of that length.
Yeah, so if we try 10 instead of 11 and it's 0, then it should be +1, because then it means it's using the path lengths as in the amount of vertices. So it just depends on which definition of length it uses.
Oh,
Yeah, so there are two paths. So we have too many paths highlighted there below as well.
yeah,
There's actually
right.
less.
Okay, fine. Okay, so then, by the way, somebody please just at least write this down? Is anybody like paying attention here? Could you like rather than me having to do this, that somebody should make sure that graph that is noted in.
Where are things like this submitted? I couldn't find it.
Bugs. Simple as that. That's the okay. Well, that's much less. Our path deviation is much less there. Okay, so this is a so our path deviation here is actually of length 10. Well, the following is wrong. 11 should be 10, but then it won't be interesting. Although your path deviation doesn't necessarily have to be, okay, so these are not geodesic paths basically here.
Yes.
But at least it gives us some sense. Okay, so let's come back down here. And that should not be 1 plus, and that's all geodesics, and that's the 2. Okay, so now what we're going to do is we're going to want for the 3 points, what's the cool way to do this? We've got 3 points and we want all 3 ABC. We want a binary function. Is that just groupings? Am I just being too cutesy by half here? That is not the right thing. Okay, come on. Somebody tell me how to get oh, it's just
does an f of
tuples.
1 do it? Oh.
What do you mean? I think it's tuples. Right? If we say tuples of this comma 2, what a mess. You know, that's going to matter. Oh no, it isn't going to matter because we have an undirected graph. In this case, we have an undirected graph, but in the future, we might not have an undirected graph. In fact, that's an important assumption at the very top here. Okay. Definitions. Initially, consider an undirected graph. And a bunch of these definitions are going to fail for directed graphs, which is what we're going to need for the causal graph case. Am I making sense? We will have to go through and generalize these again for the directed case. Okay, so what we're trying to do is, am I being stupid here? Is there an easier way to do this?
So we
just
don't
trying
want
to-
the repeats as well, right?
Case set partitions.
Say it again.
Set partitions. There's a resource function.
Subsets. We want subsets. We want subsets where there are exactly two elements, right?
Yes, that will not, well, subsets then will probably not work for the directed case, but in this case, it should give the right answer.
Right, exactly. Okay. So tuples is what we're going to need in the directed case, right? I think. And so
having self loops.
I understand, which in the directed case, oh boy, I don't even know what to think of that there. Okay, so this is the case here. So what we're going to do is we're going to say for this, this will be, sorry, this was my triangle thing. This was how to make a triangle, not how to make a webbed object. Sorry. Okay, so what we're doing here then is we say all JD6 between 50 and 100. Okay, great. Now the point 150, now we want all JD6 to every point there, correct? So we're going to take this, I'm going to take union of flatten of that, if I'm not mistaken.
So this isn't invariant on the permutation of the vertices. So if we want that, shouldn't we just basically take the union? We should take all three geodesic tubes, union them, and then just web between all of them. Doesn't that give?
Well, here, what I was
most
doing here was a
robust
different
one.
case, right? Was
Yes.
from a point to a geodesic tube.
Okay. Yes.
Okay. And so this then would be from that, then we want to say all geodesics of base obj 11, comma, and then we want to say 150 to hash for all of those. Okay. Now, what is this giving us? Oh, that's all those geodesics. So each one of those starts at 150 and winds up at a point. So what we want to do here is each one of these could be a path graph, if I'm not mistaken. So if we catenate that by a one level, do we get all those? Okay, so now I claim we want to take highlight graph of base obj 11 of a path graph. I think I want this. That would show all, see if that comes out as anything reasonable. Okay, let's try and look at this guy. Oh, computer, what are you doing, computer? Why is that taking non-trivial time? Okay, graph 3D of that. Okay, so what is this? This should be, boy, what the heck is that?
I think it uses a different color for each additional step along the line.
It does. It uses a different color for every endpoint that it's going to.
Yeah.
So
if many are on,
maybe we should pick out the original points on here as well. But do you understand what this is? This should be a fan, basically.
And do we care about the edges, or should we just flatten that and just care about the vertices in this case?
I'm not sure we do care about the edges. No, I'm not sure we do. I think that this is the content of a fan.
Yeah, so if we flatten all of that and just highlight the vertices, we can even do subgraph of that. That might at least
Well,
look
let's
better.
look at that. Yeah. All right, fine. So then let's say flatten this. And actually we can union it because we don't care about that.
Mhm.
And then we can say subgraph base obj 11. Boy, slow. Okay, graph 3D of that. Okay, what on earth is this? So that is what a fan looks like in this weird space. Quite odd, really. Okay, what is this analogous to? Is this like a wedge product, or what is this? What is this? It's a point and it's a point and a line.
So don't we want to do this? So we have a line and then we have a single point. So
Yes.
don't we want, so if we have a wedge product we have between two edges, right? So if we take this fan between each point on the one edge and the entire other line, and we union all of that, doesn't that give us some sense of a wedge product? Because at the moment we're only fanning basically at the end point, or we could do the entire edge.
I know. Well, hold on. But the question is, what is the analog of this? So this is, let's do this in ordinary space, okay? Let's just do a very simple-minded thing. So let's say we say, I mean, this is very trivial, but let's say we say a line from, let's say, the point, 1010 to, let's see, how do we get, okay, let's make a line. Who can figure out how to do this? We want something where we're going between 2 points. It's very trivial. Let's say from 1, 4. Isn't there a function that will take us some fraction of 1, 4 plus some fraction of 5, 7? Line between. Oh gosh, what is it called? Do you know what I'm saying? Line. I want to get something which has, I just want to get a bunch of points on a line, right? Which I can clearly do by writing the equation of a line and taking, discrete, a discrete parameter along the line. Yes. Do you understand what I'm talking about? I want a
Yes,
line from the point 1, 4 to the point, 20, 7 or something. Okay. How do I get? Okay, come on. This is really simple. It's
You
that
can
times
discretize
t
it.
times that 1 minus t. Right. And then what I do there is I just take that table of this. T goes from 0 to 1 in steps of 0.03, let's say. And then let's say line, well, then I could say point of that. And then I could say line from 1, 4 to 27. And then I can say graphics of that. What? Oh, that's not what I want. 14 plus 27 times 1 minus t. Okay, great. There's our line. Okay, now I want to drop things from a point. I mean, this is very trivial, guys. Very trivial. I'm not doing anything at all non-trivial here. So then what I want to do is onto this, I want to say a line from 1010 and let's say style. Okay, there is our fan, right? That is the analog of this thing here, right?
Yeah, should be.
What is that we should think about in terms of standard geometry? What kind of an object is that? I mean, it certainly has an area. That thing has some kind of area. Well, okay. So
It also has an angle, right?
it does have an angle, yes. What is its angle? What is it? What is the usual interpretation of its angle? Its angle is.
So there are two main ways of doing it. So one would be with just taking the limit as you take smaller and smaller triangles and then using the cosine rule. And then as that limit goes to 0, you're in a basically Euclidean space, no matter the curvature, and then you get the angle. But I don't think that's applicable to ours.
Right. I mean, the angle here, it should be the case. Okay. As we move that point along a geodesic, let's say we move this point along a geodesic. I don't know what the heck this does. What is it? What is the significance of the change in area? Okay, we've got our sort of geodesic fan here. This object is this thing here is so we can call this a geodesic fan. Okay, what is the significance of a geodesic fan? I mean, in the end, okay, so normally to get a triangle is a more complicated concept, I think, is it? Okay, let's look at a triangle now. Okay, so a triangle, let's say it's 50, 100, 150, okay, is all we're going to do then, okay, let's draw our triangle, although I don't think it's all that exciting. Okay, so this is, it's all geodesics of, oh, we can forget the path graph for a second. Okay, 50, 100, 150 is going to be our okay, those are all our things that are going to be, it's going to be applied to. So it's all geodesics of base obj 11 hash that thing triple at that thing there. Am I right? Anybody have an opinion about that? And I think what I want to do is I want to map path graph at level 2. Anybody? I know Nick is good at unraveling this stuff. Do you have an opinion about this?
You'll be all right.
Okay. Meet a triangle. Oh boy. Okay, so now how can we tell? Actually, what I should do here is color. Let's color each edge a different color, but not color. Do you get what I'm saying? We want to color each of these things here. How do we do that? We would say for each path graph, do you understand my question? I mean, I want to do a map thread, presumably. I've got those path graphs, and then I want to say style. Is this right? Anybody got an opinion here?
Yeah, and 3 colors.
Oops, red, green, blue. Okay. That is the most bizarre triangle I believe I've ever seen. Okay, well, it does join up correctly. Okay, so
Yeah.
that's a triangle, but we already see a bunch of pathologies here. So for example, it's a very big triangle relative to the space, but that's okay. That's an allowed thing to have happen. But clearly one of these edges was very puffed out, right? Okay, so what can we say about this triangle? We can say we could try to figure out the area of the triangle by making crisscrosses between everything. Is that meaningful?
So from my project, if you have a triangle, you can calculate the sectional curvature of it, from which you can calculate each of the 3 angles, and you can also calculate the area of the triangle in much more abstract terms.
In standard geometry, the purpose of looking at triangles is to start getting some kind of rules, which are the beginning of trigonometry. So once you have a triangle, you have length and you have some sort of dual notion of the length is the angle, and those angles have certain rules. Whether if your triangle is on a sphere or on the surface of
Right.
negative curvature or a flat space, there's some sort of rule that it satisfies. And those are the starting points of trigonometry.
I understand. I mean, we could look for equilateral triangles on our space if we wanted to. I don't know whether that's useful. But in general, I mean, in general, one is used to looking at angle deficits, right, of triangles. And for example, the relationship between angle deficits and areas and things like this. But we don't have any clue what an angle deficit is.
Yes, so you need some base thing to calculate either area or angles from, because neither are inherent.
Intrinsically. Yeah, right.
Yeah.
Okay, so how can we compute A, area, and or B, angles?
Presumably one will be related to the other.
But that depends on curvature, right?
Yes.
Sure. Yeah.
And so if you fix the one, that will determine the other, but they won't necessarily. If you fix the one in a natural way, you won't necessarily get a natural notion in the other one.
But I don't understand. Isn't it the case that the relationship between these things am I very confused? The curvature is the area, the angle deficit is the area. What is it? There's a simple formula, right? It's the area divided by the curvature or something.
Yeah, so angle deficit is pi area, angle deficit, something like that. So if you have these three things and none of them are intrinsic, so if you have two of them, you can get the other one. I argue that when you have curvature and lengths, you also define angles. And so if you have curvature and lengths, you have angles and then you have area, but there you can also do it from another direction, which I think we're currently doing, which should be quite interesting to see if it gets back to the same thing or if it gets something completely different.
But so let me just write down, what is the standard formula? I should know this. The standard formula is
Gauss-Bonnet formula.
It's a simplified version of that, right? It's the original Gaussian curvature definition. It's that okay, so there's the area of the triangle, there's side length, there's angle deficit or whatever, right? Which is pi minus the angle, sum of the angles. Okay, somebody should look up this formula. There's this thing directly determines the curvature. Isn't the curvature like the angle deficit divided by the area or something?
I think the formula I put in the chat is the one.
Sum of the angles minus pi equals k times a. Okay. So you're claiming total of angles equals curvature times area.
Total of angles minus pi. Yes.
Okay. Okay, SL is pointing out on our live stream, the geometric typical fan has only 2 points on the line with exactly 2 relations. The ends of the fan. All the others on the line have 3 relations. I don't understand that comment. Is that something about open? I mean, is that going to end up being an open set story? By the way, just to jump ahead for my benefit, I mean, right now we're still trying to define basic geometry here. We still have some issues with this. If we try to define things like open sets, topology kinds of things, what is the definition? Can somebody, what is an open set? What the heck is an open set on this thing? I mean, there's some trivial sense, right? Isn't there some trivial topology where it's just a collection of points?
That would be the discrete topology.
Yeah.
And then there's the indiscrete, which is all the points or none of them.
Okay, well, so discrete topology.
Each point is an open set.
Boring. Okay, but so now, is there any less trivial version of open sets? What is a boundary? I think given a collection of points, okay. Given a collection of points, I think we can at least define a convex hull, if I'm not totally mistaken. Well, I don't even know the convex hull. We can look at all geodesics between pairs of points. I don't know whether that's useful. That's the fanning idea again. Okay, does that object give us anything in terms of boundary versus what is a boundary? Boundary.
We had it on top, right? When we are talking about geodesic balls and geodesic spheres, We had some notion of a boundary over there.
We did, but why does that work? I don't know why that does that work more generally for a set? You know, I think we've got some notion. Okay. I think this is going to end up relating to notions of continuity on these hyperfold things. Okay, is there a general notion of a boundary? Given a geodesic ball, it's not very hard to find the boundary because we can, you know, because the thing is filled in some sense. By definition, it's filled in. But if we do this kind of fanning type approach, for every, you know, we pick all possible pairs of points. Am I making sense? Then, is there a natural definition of boundary there? I think there has to be. I think the definition of a boundary. Okay, so I'm going to claim, let's actually do one, right? So we can see what happens. So let's just pick random real, you know, 10, 6, 2. Okay. Okay, great. Now, what I want to do is I'm going to say, I want to pick line. I want to make tuples of random real 2. And then I want to graphics of line mapped onto that. Oh, I see. Okay, so that object, right? That is an analog of the thing I'm proposing doing, collecting all pairs of points, connecting all pairs of points. It's a complete graph, right? i.e. form the complete graph. Actually, is that right? Okay. No, because it'll go through intermediate points, right? The geodesics will go through intermediate points.
Yes, it's just making it a connected subgraph, I guess.
Right. But so if you look at this thing here, and you ask the question, can we tell what is a boundary point here? The answer would be anything in the volume. Yeah, we can look at geodesic balls around a point, and we can ask, okay, so a question would be, and this is awfully similar to looking at you know, open set definitions, is the whole of a geodesic ball, actually we could do that for any point, is the whole of a geodesic ball around a point contained in the region? Right, so we try and cover the region. It's like Hausdorff dimension definitions. You know, we try and cover the region with geodesic balls.
So isn't it just is all of its neighbors? Because we kind of want unit geodesic balls in our case. So isn't it just is the entire neighborhood graph contained?
Yeah, right. For unit geodesic balls, for a given point, are all its neighbors in the graph, in the subgraph, right?
Maybe another far-fetched suggestion would be to consider edges as well and say that a closed set would be something that contains everything up to nodes, and the open containing the edges without the nodes.
We're not considering the node. We don't want to do that because we're right now we're still just talking about nodes.
Okay.
So the question is, can we define an open set? You know, which set of nodes constitute an open set? Right, and what we're saying here is, but now it's a little bit pathological, because what we're saying is, anytime we try to define an open set here, the thing is going to eat itself, right? Because it's going to say, anytime we move in from the boundary to ignore the boundary, we're going to have a new boundary.
Yes, so that's why topology on these discrete spaces usually isn't terribly interesting.
Right, but we
You
need a
basically get the
generalization of that.
Yes, so we need not quite topology. We need to maybe drop one of the axioms or something like that,
Right.
or
right.
at least weaken them.
Right. We need to back off from ordinary topology because non-trivial, we won't get non-trivial quotes ordinary open sets. So now the question is, what's the generalization? Okay. What's the appropriate generalization of an open set for the thing we're looking at here?
So if I would have to hedge a guess, I'm going to give maybe something interesting, is if we want open sets, if we want any connected subgraph of the graph to be an open set, then maybe instead of having the definition where any arbitrary union of open sets needs to be an open set, it's only unions of open sets with an intersection, with a non-empty intersection. That might be an interesting way of weakening the second axiom slightly.
Okay, all right. So wait a minute. Can we weaken the set axioms?
May I ask, are we having any problems to having open sets that are both closed and open? Something also
I don't know what those are. What are
it's
those?
Open. It's closed sets that are also complements to other closed sets, so they are also open. An open set is defined as something whose complement is closed.
Right.
So in this sense, you can have
I don't know. Right.
closed set that is also open.
Oh, wait a minute. Can we weaken the set axioms? So in other words, normally you would say unions.
So normally you
quotes.
say that these operations, unions or intersections, you think of them as total operations. Now what we are saying, if we want to weaken them, what one way we might be doing them by saying that these operations should be partial operations.
In what sense?
They don't apply everywhere. So this is what I think relates to what John was trying to say, that if our open sets are now subsets, we can only make unions such that there is an intersection between them. So you cannot just arbitrarily union anything.
Right, I understand. Allow only unions of quotes open. I don't know what we call them. We call them open sets which have non-trivial, which have non-zero intersections.
In a sense, for us, a union is a gluing operation. And when one is gluing, one always has to specify an intersection.
Yes, that's a fair point. That's a fair point. So I see. Union can't just be a union of things that are completely disjoint. It has to be a operationalizable union. Okay, we are about to run out of time. I think this is, I think we're about a 25th of the way there in terms of, building up mathematical concepts, but I think that, I think this is, go ahead.
May I ask something, Stephen? Do we want to be able to define geometry in any of these objects? Or maybe we'd like to have a subclass of them because they're rather general objects.
All objects.
For all of them.
Objects like this. Basically the point is, the fundamental point is the limit is something we completely do not understand. Right? The limits of these things. In certain cases, those limits are recognizable and they're just manifolds and things. Okay? So those are all good. What we're trying to understand is there may be cases where the limit is very pathological and we don't care. But the more generic case, like this object that we'll have on the screen here, I'm pretty sure it has a meaningful limit. We just don't understand what it is. Okay. And, I think that, and so what we're trying to do is we're trying to ask the question, okay, here's a basic question for you guys. What does it mean to say something has geometry?
Yeah.
What does that mean? In other words, so for example, here's a Xerxes question. In, like in Grothendieck's conjecture, where you say there's this notion of inevitable geometry on these limiting objects.
Well, over there in the Grothendieck thing, it's not that geometry is the thing you get for free. What you get is a topology. Geometry still requires more structure. But I think answering your, so the infinity groupoid is really a topological space, not yet a geometric space. One has to do more to get a geometry. But isn't it, coming to the first question, isn't it the case that to get geometry is all about coordinatization or coordinatizability?
Mhm.
When you can start putting charts, then you start talking about geometry. Until
Normally,
that point,
yes. I mean,
it's
that's
topology.
right. Fair enough.
And right now what we are doing is we are trying to pin down this notion of open sets via geodesic balls, as in for a open interval, every sub-interval is again an open interval. So if we nail that down and we get topology at least over here in this weak, with this weak set of axioms, once we do that, then we can later on start asking how to coordinatize it by thinking of some generalizations of those epsilon delta definitions on open sets, which one can then start using to build some partial orders or some sort of coordinates.
Since we already have a metric, doesn't that kind of make a lot of that almost senseless? Because a lot of that is kind of trying to get away with having geometry without a metric, if I remember correctly.
Well, yeah, normally the normal ordering of this is, so to speak, is that topology does not require having a metric.
Yes. So if we have topology and a metric, doesn't geometry kind of just fall out of that? Or am I misunderstanding something?
Sure, but I mean, there are many types of geometries one might be interested in. Just the graph metric will probably give you one type. Maybe if you want more interesting types, you might want to admit different types of ways to put distances.
Yes, yes. So it's really interesting to see what's the if you limit yourself to path metrics, which I think is the most general, since we kind of want to have a relation to physics. Then it would be interesting to see the class of geometries you get from having some set topology with the class of path metrics, possible path metrics on the graph.
Mm-hmm.
So, okay, roadmap for this. I mean, as I say, there is a definite path that we can follow here, which we've just started to follow. I mean, we're definitely not stuck yet. There are many, many more definitions we can give before we are in a position where, where we don't have analogs of known things. I think there'll be a whole collection of essentially constructions that we can give. I mean, this is like the analog of ruler and compass construction that we're trying to do here. We're saying what is constructible using only, okay, so I make a note of that, sort of generalized analog of ruler and compass constructibility, I claim. That is, what can you construct? What can you construct with these? I don't know quite what the right term is, but ruler and compass is actually not completely irrelevant, because a ruler defines straight lines, a compass defines essentially geodesic balls, if I'm not mistaken.
Yes, so we have slightly
Part of
more
them.
where we have a marked ruler.
Yes, right.
So we have slightly more, but I think it's a good analogy.
plus geodesic ball. Yeah, and we also have a marked plus marked compass because we know how big the geodesic ball is. And so then the question is, and I don't know, this is sort of a general knowledge question I should know the answer to, how much of how far can you get in math with ruler and compass? When do you need more constructs? I mean, Euclidean geometry.
And
well,
still not the whole Euclidean geometry. Galois theory has given answers to this question, what you can construct with these two things.
I understand that has, I understand that yeah, you can't trisect an angle.
Exactly. And you can prove it with Galois theory.
Right, but what on earth is the analog of the non-constructibility of a non-trisection of an angle for what that will be? Okay, non-trisectability. Actually, I would say duplication of the cube might be better. Inability to duplicate a cube. Right, that's another one of those things you can't do, right?
Mm-hmm.
An angle, but what's the analog of that here? The analog of that would be that if that is something you cannot reach with our marked ruler and marked compass, that means it is a feature, right? It will be a feature of our hyperfold that requires additional information, that requires something like embedding information.
So usually the other thing that complicates things a bit is ruler and compass is in Euclidean space, which is very nice in terms of flatness. But I don't think the dimension is the big problem, but I think the flatness will complicate a lot of these things.
That's no doubt true, but I'm just trying to understand conceptually. The thing is, what can you not construct? I mean, Euclidean geometry, there are results you cannot reach with ruler and compass, which you can reach with sort of a more algebraic approach.
Yes.
But by that equipment, so to speak, the analog of not being able to reach something,
or even allowing more intricate mechanisms like a moving I understand, ruler. Yes.
Right, but I mean, the question is, what can we expect to construct? I mean, in the end, what we're dealing with is just like in relativity, where you construct, you use shield ladders and God knows what else of things where you just are looking at essentially light cones, where the only thing, the analog in relativity, the only thing you have is light cones. Is that right? I mean, is that, I think that's basically right.
Maybe a similar question, although not of geometric nature, is if you have a particular set of rules by which you can move in this structure, are there points that you're not be able to reach?
There aren't such rules. That's the problem. You can't make such rules because it's the same issue as with light cones and so on and so on and so on. You have a flash of light, it goes in all directions. Similarly here for us, you have a geodesic ball, it goes in all directions. We don't have that's the whole point. If we say we got a turtle moving around on our hyperfold, the turtle is going to be deeply confused because it doesn't have a notion of, turn left, turn right is not an obvious notion for it.
Or for example, move in multiples of 2 or multiples of 2 and 3 only.
Well, that's fine. If it's moving along geodesic, it's a happy turtle, but I don't think that helps it. In any case, just in terms of the map of what we need to do. So there's a definite direction of just trying to make these definitions using only essentially ruler and compass. Okay. And then the next thing is, what new notion do we need? For example, putting a function on the hypergraph will be a new notion, not of that same type. And that will allow us to do different things. And yeah, I mean,
this function must be in some sense compatible to the way the graph evolves. So if you know the function in a previous step, which should be
That's
definable.
Yes, that's true. But that's that. Okay, so yes, you're right. That's the next huge level of thing. Is one level is okay. First level is things that work on a given hypergraph. Next level, things that are somehow correlated.
Things that evolve.
Yeah, between evolving. Yeah, so in evolving hypergraphs. So an intermediate thing is things like painting functions on hypergraphs, which I think is a different. I think that's an orthogonal issue. All right, I'm supposed to go to another meeting here, so I think I have to wrap up. But this was good. Thanks, guys. This is I mean,
This event was really interesting.
What we need. Yeah, I mean, we've got a long way to go. I think we're about 1/25th of the way there. And Jean, your project. I mean, you're working on some things that directly impinge on this. Yes.
Yes, but from a different direction than we're currently approaching it. So my interest is in how, if we follow both to completion, do they give complementary or contradictory results, both of which would be equally interesting, I feel.
Yes, that's fine. I mean, from my point of view, I'm trying to just see if we were rewriting Euclid, go back a couple of thousand years, redo Euclid from hypergraphs, what would happen? Euclid and beyond.
So from my approach, theoretically, I have angles, curvature, and area defined, basically intrinsically. But the areas that has nothing to do with counts of vertices. So it would be interesting to see if there is, at least in a limiting case, is there something to do with vertices, or is it some completely different concept of area? And we're just used in integer dimensions, that those two things are kind of the same thing.
That would be cool. Right. That's an interesting thing to know.
Yes.
May I ask something before we go? Maybe just
10 minutes
question.
left. Yeah, go ahead.
Okay,
Yes,
10
please.
seconds. From a historical perspective, the generation of the development of geometry was came from the human need of having land and wanting to separate this land among individuals. What could we say is our need here that drives us and asks us for geometry? What is the end goal that motivates us to ask for geometry?
Is that existing physics, for example, and it's not just physics, because this stuff will get applicable to lots of other things as well. Existing descriptions which have been developed over the last couple of thousand years are stated in geometrical terms. So then the question is, how do we manage to leverage what is known there, what has been discovered by just essentially looking at Euclidean geometry and its small generalizations? How do we meet that from this different perspective? I think that's the basic point.
In order to understand the limited behavior of these objects, in essence.
Yes, that's the point. Yes. How does that limiting behavior? We know there are cases where these objects limit to things which are just familiar Euclidean geometry. Okay. But the question is, when they don't limit to that, I mean, this is what my sometime friend Benoit Mandelbrot could have done, so to speak, or might have done, or something. No, not really. I mean, what he looked at, oh boy, I'm somehow, yeah. I mean, what he looked at was the neighbor independent substitution system limit. Things like this that purely become nested, except that, as we talked about at the beginning, the question of calculus. Okay, I'll give you examples of things we want to be able to do. For example, in calculus, we have tensors with integer numbers of indices.
Yes.
What happens here? In other words, for example, what is the epsilon, the totally antisymmetric tensor, which has a number of indices equal to the number of dimensions of space? What does it look like? I mean, I had some definite hypotheses about these like a year ago. I think I have some. I think that a rank n tensor is a thing that starts from a point and has sort of n-geodesic tentacles hanging out from it, and that the totally antisymmetric tensor is like saying how many tentacles can you have before you run out of room to put in tentacles, and that effectively is telling you the dimension of the space, and that's why the totally antisymmetric tensors are, that's how that whole thing comes together. But we need to work this out in more detail, and I need to go to a completely different meeting. But to be continued for those interested.
Thanks,
This
Stephen.
is this will show up in the public archive of current files by tomorrow. Okay, thanks a lot, guys. Thanks to folks on the live stream. You guys have been a bit silent today, but thank you for your comments here.